Hello, everyone. Welcome to Theo-MathProblemSolver. In this particular episode, I'm so excited to take you through the journey of second order linear equations. Now, a second order linear equation has the form, or to be most, general in nature, we will say that it has the form um, p of x, then the second derivative of y with respect to x plus some continuous function multiplying the first derivative with respect to x plus another continuous function multiplying the dependent variable y equal to some continuous function, let's call it g of x. Now, as I mentioned, p, q, r, and g are continuous functions. Now, in this section, I want us to study the case where g of x is 0 and another case where g of x is different from 0. Okay, so we make a deduction here that we made a deduction over here that for g of x equal to 0, so let's call this one, let's call this equation 1. So for g of x equal to 0, then we can make some deduction here. So I'd want us to take our time, then we'll do that. So when g of x equal to 0, then we're going to have p of x multiplying the second derivative of y with respect to x plus q of x multiplying dy dx plus r of x multiplying y equal to 0. But then what is the name of this? How do we call this if g of x is 0? If g of x is 0, then we claim that such an equation is what we call that homogeneous. We call the homogeneous linear equation. This is what we call the homogeneous linear equation. That's for the case when g of x is 0. What happens to the converse? If g of x is not 0, what is the name? Now, if g of x is different from 0, then it's what we term as the non-homogeneous linear equation. Okay, so if g of x being different from 0 for every x, then we claim that equation 1, then equation 1 is called non-homogeneous linear equation. Okay, good. Very, very important. So it's important that we understand all of these. Now, another, two basic facts that we need to understand as far as differential equations concern is that sometimes we can have functions that satisfy the differential equations. Now, suppose we have two solutions. Let's say solution one, solution y1 and solution y2 of such an equation. Then what then happens? Can there also be a solution to the whole general solution? Can it be part of the solutions? If they're able to satisfy such a solution, do we also call them that? Then we claim that their linear combination, okay, so linear combination I will explain later as we move along. I will explain it as we move along. We said that the linear combination is also forms a solution. If solution y1 and solution y2 are solutions of the ODE of the homogeneous linear equation or the non-homogeneous linear equation, then their linear combination will also be part of the solution. Okay, so let's move to a theorem. So we move to a theorem. So in this theorem, we say that if y1 and y2 are both solutions of the linear homogeneous equation, okay, so equation one, then C1 and C2 are any constant. Then we claim that their sum, which is these two solutions, okay, now becomes a solution of equation one, okay, which is very, very, very important. Remember that this is our equation one. So we claim that if y1 and y2, solution, let's look at this, let's call this one equation two rather, not one. So equation two. So if y1 and y2 are both solutions of the linear homogeneous equation of which we are referring to this particular solution, okay? So we are referring to this particular equation. If they are solutions of this of equation two, then we are saying that their linear combination, okay, also forms a solution of equation two, okay? So linear combination, um, it just means that we can, sum the solutions, and once they are summed, we can write it in a way that it's in a such a way that they are also a solution of the homogeneous linear equation. Okay, so this is how we write the linear combination. Now, for I think I would like to do a quick proof on that. I think that would make everything simple. So let's get some proof for this particular one. So let's get some proof. The proof. Now, since we can say that since y1 and y2 are solutions of equation 2, okay? If that's the case, then we have that. So since there's y1 and y2, are solutions of equation 2, remember this is your equation 2. So it means that they will satisfy this particular equation, right? So in which case we're going to have p of x y1 y prime prime. Instead of using the y dx, I'm using prime prime. Okay, for for ease of illustration. Okay, then plus r of x multiplying y1 equal to 0 because they satisfy the equation. Okay, and remember we also have another solution which is y2. Okay, so in other words, we're going to have p of x multiplying y2 prime prime plus qx y2 prime prime plus r of x multiplying y2 and should be 0, right? Now, over here, we will just have to apply the basic rules of over here, we just have to apply the basic rules of differentiation. And that by using the basic rules of differentiation, so which means that we are going to have so it means that our p of x y prime prime, which is the main homogeneous linear equation, qx y prime plus r of x y should be equal to Should be equal to what? Can somebody help us here? Now, it should be equal to P of X. Now, what is your Y? What is your Y? Our Y, remember that since y1 and y2 are solutions of the linear homogeneous equation, it means that we can write them as a linear combination this form, okay? So in which case, we can replace the y by c1 y1 plus c2 y2, okay? So it means that we can do that. We can confidently do that. So in which case, we can replace that by this, okay? And then we have q of x. Then we open the bracket, and then with y1, with y prime, we are going to replace it by what? By c1 or c2. So we are using a y1 right now. So c1 y1 plus c2 y2 prime plus r of x multiplying our y is what? Is c1 y1 plus c2 y2. Okay. Now, what do we do here? By applying the basic rules of differentiation, we should be able to have what? You should be able to have P of X. Now I'll just run through the prime. So we're going to have C1 Y1 prime plus what? C2 Y2 prime. Okay, plus QX. They're just using the basic rules of differentiation. Okay. So we're going to have C1 Y1 prime plus C2 Y2 prime plus R of X C1 Y1 plus C2 multiplying Y2, that right? Now over here we can sort of do some groupings, right? We can do some grouping. So look at a situation where we have the Y1. So we can separate the C1s from the C2s, okay? So we are going to do some collections. So wherever I see C1s, okay, I try to sort them from the C2s, okay? And if you take your time and do it, we should have C1 outside, and we're going to have P of X multiplying Y1 prime plus Q of X Y prime 1, okay, plus R of X Y1. And then we also have the C2. So we have one C2 here, another C2 here, and then the last C2 here. So we are kind of collecting them, okay? And then factorizing that. And by doing so, we're going to have all right. Now remember over here. Now, what do you think will be here? What do you think this result will be? This result will be what? Will be 0, okay? The reason is because we've already stated up here that this is already 0, okay? We already stated it here that this is 0. And the reason is because y1 is a solution of the linear homogeneous equation, okay? In which case, wherever I see it, I can replace it by 0, okay? Then plus C2, and this one will also be what? will be zero because it's a linear homogeneous equation. Okay, zero. So in which case we're going to have zero. And since this has been able to, satisfy the equation, we've been able to prove that indeed the linear combination, which is which is C1 multiplying Y1 plus C2 multiplying Y2 is indeed a solution of, it's also a solution of the linear homogeneous equation. I hope it makes sense. All right. If you have any comment, concern, put it in the comment section and I would attend to you. So let's move to another interesting concept, which I believe that those taking ODs would benefit a lot. Now, it's important that we kind of, since we are talking about solutions of linear homogeneous equations, it's also important to look at other interesting things that sometimes arise in the course of solving problems. Now, in this theorem, we claim that if y1 and y2 are linearly independent solutions of equation 2. Remember, the equation 2 is the linear homogeneous equation, okay? And p of x is never zero. Remember that this is your equation, equation 2 we are talking about. This is equation 2 we are talking about, okay? This is equation 2 we are talking about. If we claim that p of x is never zero, in other words, the coefficient of the second derivative is never zero, and it's never so, then we claim that the general solution can also be written as a linear combination, okay? Can also be written as a linear combination where we kind of use the same statement that or the same rule that, or the same condition that C1 and C2 are arbitrary constants. So they are not functions, they are just any constants, okay? Could be some rare numbers, so to speak. Yeah. So let's look at other interesting things that we can take from here. Now, this is very powerful because if we know two particular linear independent solution, then we know every solution, right? Yeah. So in general, sometimes it's not easy to discover particular solutions to a second order linear equation. But it is, always possible to do so if the coefficient, which is P, Q, and R, are constant functions. Okay, if they are constant functions, and if the differential equation has the form, let me be more definite here. If the differential equation has the form, let's say A y prime prime plus b y multiplying y prime plus c is equal to 0. So in which over here, our a, b, and c are just constant instead of, like the p, q, and r that we said they are continuous functions. Okay, when they are continuous functions, as I mentioned, they are very difficult to solve. Okay, but once a, b, c are just arbitrary constants, they are easily to be handled. Does that make sense? Good. Over here, we also want to state that we want to, it's important to point out that A should never be 0, okay? Should be different from 0, okay? Very important. Now, so how do we then solve such a problem? Now, so over here, we are looking for a function y such that a constant times its second derivative, okay, plus another constant y prime plus a third constant times y is equal to 0. So I'm just saying that I need a function that can behave like this. Okay. So that's what I'm trying to say. Now, if you cast your mind back, we've learned about exponential functions. If you have been, following us over the months, we've been talking more about exponential functions and how they are very, applicable in real life, in the area of diseases, in the area of banking, all of these things are exponential function play a very key role, right? Yeah, and there's something particular about exponential functions, and one of the properties is that its derivative is a constant multiplied of itself. Okay, if you remember very well, we said that for exponential function, let's say exponential function, um, let's say y equal to e to the power, let's say r of x. Okay, so the r is just a constant. Okay, remember that the first derivative of this exponential function is always what, a constant multiplying um the function itself. Okay, okay. So we say that the exponential function has a nice property, and that property, the property we are talking about is that its derivative, okay, is a constant multiple of itself. It's a constant multiple of itself. Okay, it's a constant multiple of itself. Very good. So let's take note. Then what then becomes the second derivative? So we see that the second derivative now becomes what? Becomes r squared multiple of itself. Okay. Very important. And this is a very interesting property for exponential functions. And we are going to leverage this to solve a whole lot of problems. Okay. Now, such an equation. So for example, now if we are going to, if for example, if we plug this into this, if we plug this back, if we plug all of this, oh, if we plug this into back into this, then we are going to have an interesting result. And what is the result? Let's take our time to go through everything so that we understand it better. Now, when we plug these, all of these, the function itself, its first derivative, and its second derivative back into this, we are going to have, so we are going to have, so it means that wherever I see, so we have A. So when we do that, so you're going to have A. Then wherever I see y prime prime, y prime prime, I'm going to replace it by r squared E multiplying E, A multiplying r squared times the exponential function, okay? Then plus, now the B, now what is my y prime? My y prime is r multiplying the exponential function, okay? Then plus C equal to what? Equal to what? 0, right? Now there's a y here. Sorry, there's a y here. Equal to 0, okay? Good. Now, over here, we see that we can just do something. Okay, so we can factor out the exponential function out. Okay, we can factor the exponential function outside, and by factorizing that, we are going to have this. Okay. Um, remember that there's no way the exponential function can be 0. Okay, so over here we wanna say it, or kind of point out that the exponential function can never be 0, but um this quadratic expression can be 0. Okay, it's very important for us to note this. Okay. Now, I want to point out that this quadratic equation, which is um which is a multiplying r squared plus b r plus c equal to 0. And this is what we call the auxiliary. Okay, the auxiliary is what we call the auxiliary the auxiliary equation. Some books will say characteristic. Okay, in some book they will say characteristic characteristic equation. Okay, very important. Of the differential equation, which is a multiplying y prime prime plus b multiplying y prime plus cy equals 0. But notice that it's just an algebraic equation that is obtained, from the differential equation by just replacing y prime prime by r squared, y prime by r, and then y by 1. Okay. But sometimes the roots, which are, um, R1 and R2 of the auxiliary equation can be obtained by factorizing, okay? Or by just factorizing okay? In other cases, they are found by using the quadratic formula, of which we are familiar with it. But I just want to, point out that over here, in this case, y being equal to, y equal to e to the power rx is a solution of this particular equation. Okay. Okay. If r itself is a root of the equation this. Okay. Note this one. Okay. So if r is a root of the equation of this party or of this auxiliary equation or characteristic equation, then we claim that y equal to e to the power um, rx is a solution. Okay, very good. So let's take note of that. It's important that we understand this.